Hey everybody. So the last thing we left off talking about was the formation of aldols from both an acid and a base mediated pathway. Aldols themselves are pretty hard to isolate because the aldol and the conditions it takes to form an aldol, the aldol usually reacts fairly quickly to go on to the aldol condensate. Acids will do this faster. Acids will do this reaction faster than bases will. Bases, it's slower, but it still works, ladies and gents. It still happens. So let's look at how the condensate forms. We were here with our acetaldehyde using the base pathway, I believe, and what we had was this. Now, let me double check that real quick. Yeah, that's right. All right, so we got our aldol condensate there. Or rather, our aldol product. The condensate happens like this. And I know if this doesn't offend you, it should, because we just kicked off hydroxide as a leaving group, which I have been telling you for years you cannot do. But guess what? You can in this case, mostly because your product is very stable. The further you can smear those electrons around, the better. Now, let's look at the acid pathway. I didn't use that, though. I used this in my example. Remember, the phi is an aromatic ring. By the way, if you choose to do this on a quiz or exam, you don't have to tell me what the phi stands for. The only other thing I can think of that phi means in chemistry is dihedral angle, and I'm going to just assume you don't mean that. All right, so that OH is going to get protonated by another hydronium, putting you here. Then water deprotonates and you wind up with your aldol condensate. You ever notice how I'm always running out of room? Now this one is especially stable because it can also push electrons through that aromatic ring. More on that next chapter. All right, so this was the aldol condensate. It is, you can, in some circumstances, isolate the aldol through the base pathway. It's rare and it's really hard to do, but you can do it. In this case, in the acid pathway, you cannot do it. You cannot stop at the aldol. It will push straight on till the aldol condensate. Now, there's one other way of forming an alpha-beta unsaturated carbonyl. And let's do this. Butanal. Stop giggling, Kai. You're a little old for that. Butanal. And let's react this with HBr. This is from a couple videos ago. And Br2. Well, this will be a monohalogenation. How could you know that? Well, one, it's acidic, and you've got HBr and Br2, meaning this is what you get. In case you were wondering why we care about any of this, this is the reason. Because now you can bring in base. Pull that proton off. This is an E2. And your product is sweetly stable because of the ability to conjugate through that carbonyl. All right. Now, more on these in a few minutes. You know what? More on them right now. Because sometimes you can do some fun things like this. All right, so let's have this diketone. 2, 3, 4, 5, 6. Folks, if in doubt, count your carbons. I do it all the time. And we're going to react this with a base. And what we're going to form is a cyclized product. Now let's see why. So there's our diketone, and we introduce this to the base. This is the enolate we are going to use. More on why as soon as I get done drawing the picture. I swear, some of you have no patience at all, Alex. Okay, this is the enolate we're going to use, even though that flies in the face of what I just told you about the other enolates. So here is why, and we're going to work through the example down here of using the more substituted enolate. All right, so the one we have here, we reform the carbon-oxygen pi bond. You do an intermolecular cyclization, attack the carbon, open up the pi bond, which puts you here. And I am going to use a trick that I use whenever I do these. I'm going to number my carbons. So when you get into your product, you can do this. 1, 2, 3, 4, 5, 6. So you know this carbon here has the OH. We've already grabbed the proton there. It's not that exciting. And the methyl group hanging off of it. This is a 6-membered ring, which means it is favored to form. This one down here, we try to do the same thing. We have a 1, 2, 3, 4-membered ring. Very much not favored. So it would look like this. And that is not going to happen. So really quick, let's go ahead and dehydrate this. And here's what we make. There's the alpha-beta unsaturated carbonyl that you can work with here. Ladies and gentlemen, this works to form 5 and 6-membered rings. 4, it's really hard to do. 3 is impossible. 7 gives you a lot more flexible variations that make formation of this ring hard. Believe it or not, the next easiest one to make is 12. And I've never understood why. I think there's something magic about a 12-membered ring and the geometry it can form. All right. Now, how do you know this will happen? How do you know that we're going to be doing an aldol cyclization here? So, when to do an aldol cyclization. 1, you do an aldol cyclization when you have a dicarbonyl. 2, you do an aldol cyclization, or at least you should think about an aldol cyclization, when you've got a dicarbonyl and no other electrophile. All right? These are the 2 times that you should think about this. If I haven't given you another electrophile to play with, then you need to be doing this. All right? I'm going to stop at 10 because we've done aldol reactions, we've done aldol cyclizations. It's time for us to give the esters a chance. And maybe finally I won't screw up the acetoacetic acid video one more time. All right, folks. See you soon.